Okay, today, we're gonna move on to section, 1.2 today. I know that we have homework page 8 that's due today, so that should be in the basket if you haven't turned it in already, unless you're gone, so that's understandable, but, just make sure if you haven't turned in page 8 that gets in my basket today, make sure your name's on it, date, period number, pages, that type of stuff, so that was due today. Okay, other than that, let's talk about the section we're in. We're in section 1.2. I think we introduced this last Friday. It was called segments. We're going to go through that today. We're going to go through the formal definition one more time of what a segment is, and then we'll talk about the properties and all the little details about this. So, again, main goal. Let's talk about the definition of a segment, what it is, what does it look like. We'll talk about notation with that. That's kind of a big deal. It's kind of a big deal throughout the whole chapter, notation itself, because that's the thing is I really check for in your homework. So, what the homework could potentially look like. So we'll go through a couple of properties of what you'll need with that, with the notation, the properties. There's one postulate that we need to talk about that I believe we introduced Friday. But we never even got to see like an actual homework problem. Like, what can you use that for? What would it look like? And that's kind of the goal. And then we'll finish with some examples of particular things we can use it for. So hopefully today, we can get to a point where we can actually try our first construction in geometry. There's 14 different constructions that we learn throughout the year. And there are certain times when I'll introduce them. Today we're going to learn our first one. Okay, so we're going to do, hopefully today we'll get to that. We'll get to construction number 1. In previous years, I've saved the constructions for the very end of the year. We just kind of do them all at once, but some of my students from previous years said it'd be nice if we learn them earlier. Then we can use them when we start drawing pictures in homework when they require you to get something like a scale model of it. So we're going to do those early. So hopefully we can get to our first one today. All right, so does everyone understand the outline we're getting today? No homework or anything like that today. It's just kind of notes, some basic stuff. We'll see where we get to. Okay? All right, just a reminder, homework, if you haven't turned it in, and if you borrowed a book from me, make sure you get those back. Shipment's supposed to be in this week, so then you can keep your book, and we'll get you the online version at some point this week, maybe hopefully by Wednesday. Okay? All right, any questions, concerns? Perfect. Okay, let's jump right in. Let's start with the definition of a segment. And I believe we had this on the board on Friday, so unless you were not here, you probably wouldn't have this. So. All right, so segment. It is a type of line, that's what we need to realize. It is one of the 3 types of lines that we've been learning. It's a type of line. Its actual formal name for it that we discussed, it is called a line segment. That is the formal name. I'll usually just refer to it as a segment, but its actual formal name is a line segment. Now, let's get to the definition. We'll draw a picture, we'll look at some notation, we'll look at some different things with that. So, it is a geometric figure that represents the distance between two points and has 2 endpoints. So it represents the distance between 2 points, right? And it has 2 endpoints. Now what we talked about on Friday was that an endpoint is it literally starts and stops somewhere. There's no arrows. It doesn't continue in both directions, not like a normal line would. This is the second type. Segment start and stop. That means it's measurable. That's what you need to realize. It is measurable. So let's discuss that drawing here. So 2 points here. I believe I used the same letters on Friday. We used A and B. Something like that. Starting and stopping. Point A and B. Okay, notice no arrows. Now, here's the weird thing, okay? It is measurable. It is measurable, but the weird thing to me is that they would say that there is a potential to have an infinite number of points on that thing. And that's a little mind-boggling. That, okay, you can see there's a certain stopping point, but potentially, because of some axiom in math, there is potentially to have an infinite number of points on that little segment there, that little stick. Because for every point you label, there's always one next to it. So what I mean by that is, if I pick A and C here, okay, that's a small segment, there's always a point in between it that I could choose. And then whatever I pick for that, say I use letter D, there's always another in between those two then. So there's an infinite number because you can get to microscopically small because points have no measure. They're just small, they represent the one location. But that to me, it's a little silly. I understand the concept there that there's always one in between another. But for me, it is measurable. There is a distance here starting and stopping. Okay. Now, the notation for this that you need to get used to, you have to pick the two letters. Actually, we use the outside letters if you're using the whole stick. So you pick A and B or BA, doesn't matter, and you put a little bar above it. Now again, last week we discussed that for a segment, notice there's no arrows, just a bar, or the book could do this. They might just leave the bar off the top. Now the subtle differences between the notation here is that this one, typically when the book writes it like this, they're actually just talking about the distance itself. Maybe that's like 12 inches, it's a foot long, that type of thing. As opposed to when they use the bar above it, they're actually talking about the drawing and the distance in one. They're both the same object. So it's like the drawing versus just a number. I prefer the bar, just so you get to know that. So that way you're really identifying that it's a line segment, not a line continuing. Okay, any questions with notation, the actual definition? Okay. The other thing that we talked about last week was that idea that you could use italicized abbreviations. So for instance, they could call this segment here, they could call it segment L. These little italicized letters. That was another way you could do it. You could label a line or a segment with an italicized letter. It's not a point, it's a label. And you'll know those italicized letters when you see them. It's actually the name of the object. Don't call this segment LB. That's silly. We don't do that. Because that L is the actual name of the object. It's not a point on it. But again, it's cursive letters, so those are your three options there. You can switch the letters around if you need to. Alright. Questions, comments, concerns? Okay. Here's the thing. We discussed last week, we talked about the line. The line itself, the one with the two arrows on each side. And I'll put some points down here. Let's call this C, D, E, and F. Okay, so lines can have a bunch of letters. Same thing with segments. They can have a bunch of points on them and labels and stuff. Lines, it doesn't matter what letters you pick because it's infinite in length, so it doesn't matter which one of the four that you pick here. You just pick two of them and you put the little arrows above it. On a segment, if you're talking about a specific length, you have to use the outside letters. Okay, so if you're talking about the whole stick itself, you have to use A and B. If there's some point in the middle here, and I don't know what letter I used earlier, but I'll just use G here. You can't just pick any of the three letters. You have to know what size of the segment you want. So you want the whole stick, you want a little piece of it. That way you have to use the outside. So if you want the smallest piece here, what's the smallest piece of the segment? AG. Those are the letters you have to use. You can't use just any of the three. It's not like this one over here. This one doesn't matter because we don't measure lines. Okay? So that's just a little subtlety. It's common sense. Most people go, well, duh, that makes sense. I understand that. The other thing is, on lines itself, there is a bunch of segments here. There is segments inside that line. There's an actual segment from C to D, there's a segment from D to E, and E to F. So if you're talking about those, that's fine. You can break up a line into multiple segments, but you just need to realize that lines, we don't really measure that, but there is segments inside of it. So, connecting points. Okay, now, let's talk about the idea of the properties we can do here. So we'll get to that first postulate we talked about, and I'll give you the formal name, and then we'll talk about how we can use it for potential homework problems. So that postulate, I don't know if did we give it a name on Friday? Did I tell you what it was called? Did I say the segment addition postulate?
Mm-hmm.
Oh, perfect, okay, so the first postulate we're gonna talk about, postulates again are assumed truths in geometry. It's a property that's so basic, it's so simplistic that it's an assumed truth. We don't have to prove it. It's something that it's like a basis of math we have to start with, right? It's like your basic facts you learn when you're in elementary school. They teach you how to add, subtract, and multiply. They don't really prove anything. It's just we have to start there, and then we start to get to higher level mathematics off of that. Well, this is the idea. Postulates are so basic in nature, we have to start with that, and we can use that for later purposes. So the postulate we're going to learn is called the segment addition postulate. And so it's called the segment addition postulate. And what it states, and it actually just gives a formula. It says let B be in between points A and C on segment AC. So let B be in between points A and C on segment AC, and then this is the case. Then dot, and I'll give you the formula that they're talking about. And I'll give you the drawing too, because obviously no one would really know what a postulate means unless you saw like a little drawing next to it. But here's the actual formula. AB plus BC is equal to AC. That's the actual postulate that they state. It looks like a little formula. It is, right? It's a little equation that we can use. You can add two segments together, makes a bigger segment. And obviously the drawing that goes with it. So we have a segment A to C, that was required. That was stated in the instructions above. And B is somewhere in between. Doesn't matter, it doesn't have to be perfect middle. It can be anywhere you want. I'll put it here, doesn't really matter. You can put B wherever you want. And now what they're stating is that when you add the two small pieces together, so this is segment AB, that's A to B, and this is BC over here, it's the smaller one. You can add the two pieces together, makes the full stick A to C. Common sense, right? Duh. One stick plus the other stick makes the whole stick. Now, there's actually a lot going on here, because it's stating that you can't have a bend in the road. There can't be a flex to it. And this is the part that I believe we got to on Friday right before the bell went off. That this is how you show segment addition, how you add segments together to make one segment. Not a triangle of dots, a straight line of dots, a segment of dots. Okay? That's the concept. And then what I was trying to explain on Friday was why this is very specific in drawing. Why couldn't we do this? Here's A to B, and here's B to C, and use the same formula, right? A plus B plus the other one B to C, and then going the final distance, AC, right? Well, here's the idea. This is AB, this piece right here, that's AB. This is BC, right here. AC on this formula, right here, this formula, AC is actually this part. This is AC. Even though it's not drawn, that's AC. When they use segments, and they put a little bar above something, they use two letters, it's the shortest distance between the 2 points. You don't make an L shape. You don't go around the block. That's what this is stating in that formula. It's the shortest distance from A to C. So the idea is that that formula right here, this segment addition postulate, this little equation here, does not apply to this drawing. It doesn't work. The reason why it doesn't work for this is because it's called the triangle property, right? This triangle rule. And imagine that you're standing right here. I'm going to draw a very terrible picture. So here's you. You're standing right there. And your house is over here. So here's your house. Okay? Little detail. There you go. There's your house. Yeah, you got a chicken. Okay, there you go. So the idea is that you want to get home. So you could either walk A to B and then B to C, so you're walking around the block, or you're just going to walk through the backyard straight to your home. Which one's the shortest distance? What would be the shortest path? You walking around the block or walking straight through the backyards? Straight through the backyards, as a crow flies, right? Straight line. That's the shortest distance, that's AC. That is not the same distance as somebody walking around the block. Walking around the block is too far. It's too many steps. You can see it. You walked a further path than the straight line. This picture shows why the formula only applies to this thing right here. It only applies to segments. That you can add segments together to make a full segment if they're in a straight line with each other. This rule right here, this picture, actually is a proof if you have a triangle or not. That's how you can tell, like when you're looking at a picture in like a maps testing or an ACT or whatever like basic like standardized test you're taking. Are you looking at a triangle or is it a straight line? Maybe the picture's deceiving. Because if they do this, where they say, you know, AB is 5, BC is 2, and AC is 7. AC is 7. So the idea is that we can actually use this postulate here to prove, is it a triangle or are you dealing with a straight line? So you just plug these numbers in on this picture and see what happens. So here's AB, here's BC, and AC is 7. So what type of drawing do you have there? Is it a straight line or is it a triangle? Straight line, because the two smaller pieces added up to make the third one. You know you're on a straight line, because that's the postulate, that's what it's stating. Okay? If it was this situation, let's go with like 6 here, where they're stating, you know, AC is 6, now you have a problem. Because now it doesn't make any sense anymore. Now you're in that situation where you went A to B is 5, BC is 2, and all of AC is 6. It's this picture. It's not a straight line anymore. The AC was actually a shorter path than going around the block. How that works for the triangle property is that any two walls, doesn't matter which two you pick, any two walls out of a triangle should always add to make a number that's bigger than the third wall. No matter what two walls you pick, it should always be more than the third wall. That's something that a lot of geometry students and a lot of like upper level mathematical students don't understand. They don't realize it has to be that way. So throughout this year, I know I'll do this thing where I'm like, hey, throw out a couple numbers and I'll just put them on the triangle and we'll find a problem that works, right? They never really think about there's a certain stipulation for a triangle. Two walls have to add to make more than the third. So let's make up some numbers here to see if you guys are paying attention. So what does AC have to be?
6.
Yeah, it has to be less than the other two added together. Has to be less than the other two added together. So this wall could be 6 for all I care. Could be. I don't know if that really makes sense, but it could. Maybe this is really tall. Maybe this picture is deceiving. But any two walls have to be more than the third. So when I add these two walls, when I add those two together, do they make more than 8? The other wall, the wall that I didn't choose. Yeah, so that works. If I add these two walls, does it make more than the 7? Yeah, so it doesn't matter which two you pick. Okay, now, so you guys chose 6, right? That's fine. This is the number you guys kind of created. What was the minimum number that it had to be? Well, that was the maximum number. Yeah, maximum. I agree. The maximum you could have been was 14. Couldn't take 15 because walking around the block shouldn't be the same distance, right? So the maximum number could have been was 14. That's good, or 14 and a half, 14.9, somewhere in that decimal range. What's the minimum number? The smallest number I could have put here?
2.
Yeah, just above the number 1. Had to be bigger than 1. Here's the concept. Here's why. This number has to be bigger than 1. If I put a 1 here, what happens when I add these two together? Yeah, it makes 8. The other wall. That means it's not a triangle, it's actually this situation. It's actually a straight line. So in fact, if that was 7 and this is 1, that means it's this type of thing. Where, say this is B, this is A, and this is C. Or this is 7, this is 1, and now the whole B to C is now 8. That's the idea. It's not a triangle anymore. So we have this idea that we can show like what type of numbers you can put here. It has to be bigger than 1, because 2 walls always have to make more than a third. So it has to be bigger than 1, so it could be 1.1 for like here. And the maximum number, like you said, was 14, right? 14 or some decimal around that. Couldn't be 15, because 2 walls have to always be more than a third. That's something that you just need to realize right now. But this is the property that states why all this works. Okay, now let's talk about the homework problems you could potentially get here. Like, what could they throw at you where you'd have to use this? Well, it could be a situation where you're doing some basic algebra. Maybe they give you a picture like this, and they want you to find the missing wall. And maybe they're giving you some algebra facts. So they're going to state that maybe AB, let's say AB is, let's say that's a 2x. AC is a 4x plus, let's say 4x plus 10. And we want to know what BC is, right? It could be an algebra thing. It could be a thing where you're trying to figure out, okay, what is the question mark? It could be just an algebraic expression. It doesn't have to actually be a number. It doesn't have to be like 15. It doesn't have to be a number. It could be an expression. So I can use these facts to actually figure out what BC should be in terms of algebra. Okay, so here's the idea. So here's AC. Let me highlight this. This is AC. That's the whole thing, right? AC is supposedly a 4x plus 10. AB is supposedly, this is a 2x. So what would this have to be? What would be left over to make this thing work? Well, to find BC, all you have to do is subtract these two. Subtract them. It's whatever's left. Because they have to, these two pieces right here, the two smaller pieces, according to this formula, these two have to add to make that thing. So what would this thing be? What's left over when you add this plus this to make the 4x plus 10? What, somebody said? Yeah, this part here has to be a 2x plus 10. Because think about it, 2x plus 10. When you add these two things together, they should make that. And does it, when you add those together? Yeah, so it works. So that's the idea. It could be just an expression, like you just need to find this piece. Sometimes they'll ask you to solve it. Maybe they give you all of this and they say, hey, solve, figure out what x is. Well, then you have to set up the actual formula, to set an equal and solve. Obviously, you couldn't do it for this problem, but they could give you variables and they could give you numbers and ask you to solve for something. Okay, it could be like a situation like this. Let's go back to the original. So they could say, okay, AB here is a 5x. This is a 3x plus 8, and this could be a 48 up here. And they might say like find x, that makes this thing work. Okay, well, and the 48, by the way, is the whole thing. So to solve that, to figure out x that makes this thing potentially work, you add the two smaller pieces, AB plus BC, and that makes the whole stick AC. So 5x plus the 3x plus 8 equals the 48. and then we can solve. Now you can add these two together, because again, it's like terms, it's algebra 1. So you add like terms, you can add the x's together, so that's 8x, 3x plus 5x. And then I can solve. Now, can I add these two things together? No, don't do that silly mistake where somebody looks at it and goes, oh, that's 16 x's. No, it's not. This doesn't have a variable in it, doesn't have an x. That one does. They're not like terms. So what you need to do is you need to get rid of the 8. You need to take it to the other side. How do you take the number across to the other side? What happens?
Subtract.
Yeah, you subtract. You always do what we call an inverse operation, right? You do the opposite to the other side. So if I drag it across the equal sign, that's the only time you'd ever do this, by the way. If you drag it across the equal sign, you do the complete opposite to the other side. So I'm going to actually, instead of adding 8, I'm going to actually subtract 8 from the other side. Now, the reason being, like, why you do that, why I would drag that over, is you want to get the like terms next to each other. The 48 and the 8 are like terms. They're the same digits, right? They don't have variables on them. So I subtract 8 off the other side. In fact, the real mathematics here is not actually dragging it to the other side, it's actually doing this. It's actually subtracting 8. It's called balancing, right? You're balancing the equation, so you have to do the same operation to both sides. So I'd subtract 8, these would go away. And then the 48 minus 8 would make what, 40 over here? And then what? Yeah, because you divide by 8, right? I do the opposite to the other side, because that's actually what you're doing. You're actually doing the opposite of multiplying the x by 8, you're doing the opposite to the other side. I'm dividing an 8 over. So this actually turns out to be 5. And that's what makes it work. In fact, this stick here, if I plug the 5 back in, this stick is 25 in length. This stick over here is what? 15 plus 8, so it's whatever's left. So, okay, is there any questions with that? Like how you potentially do this? Okay, that's something that's expected. I mean, that's something that will be in our first assignment. We'll probably do more examples of it tomorrow. But I just want to make sure that you're comfortable with that. Because some people, like, they get to this type of stuff, and then they don't know what they're doing anymore. That makes me a little worried, right? Because you should have passed Algebra 1. So you should be fine with this type of mathematics. Okay, now, in this class, at some point, we do cover some basic algebra facts. We do cover, basic properties of mathematics, how you'd actually subtract to both sides and solve it out. So I just want to make sure that, is everyone comfortable with that for right now? Okay. If you're not, that's something that we can definitely work on. You can come in the morning after school, come during one of your study halls. I can overcome just some basic stuff where you're comfortable and you always get the right answer every single time and you're not getting wrong answers and you know what to do first when you look at a problem like that. Okay, that's the type of stuff you need to be comfortable with. For sure, when we get homework tomorrow, you're going to have a couple problems like that. Just a few. Okay, I'm not going to give you a lot. Okay, any questions with anything we've talked about so far? Alright, so hopefully this isn't scaring you too much. Hopefully it's pretty basic. Alright, now, let's talk about what I want to go into. I want to go into this idea of constructions. What a construction is. Okay, so you definitely need your notes. I'm going to hand out a couple tools here so we can actually go through this. This will be our last topic today. Alright. 4, 1, 2, 3, 4, 5, 7, and you go 5. Alright, you're getting some rulers. I know they're in rough shape. It's a ruler. I know. Try to resist the urge to scribble your name on it or draw on it. I don't know why it's I hand those out and the first thing people want to do is sign their name to it. It's not yours. Don't sign your name on it. Okay, next thing you're going to get, a geometrical compass, right? Okay, this is a compass, not a protractor. Know the terminologies. This is a compass. Okay. the one that doesn't have a little plastic tip, let me know. There it is. Found it, never mind. There's actually a ton of them. More than I was figuring. Okay. Oh, tips on these things. Okay, keep those back. Those are good. Alright. And I got a few more. These are the ones I wasn't hopefully going to get up today, but might have. How many more people need compasses? Okay, 2 in the back. Okay. Perfect. Alright, and then you guys get these. So, these are ones I was going to bring up tomorrow, but not today. Okay, you can open them up. Don't lose anything, just a little tab at the top, pull it out. I think there's already lead in it, so you don't have to worry. Watch your finger, that metal spike on that thing is incredibly sharp. So don't poke yourself with that thing. Okay, I don't want you getting tetanus from a geometry compass. Okay, alright. Hopefully tomorrow everyone will get these. I wasn't planning on handing these out until tomorrow. I like to keep them brand new when we need them. Alright. These tools are the basic tools for doing constructions. That's it. It's a straight edge. Not even supposed to be using a ruler, right? You're supposed to be using a flat, straight edge, where you're actually supposed to look at the side without numbers on it. Because if you look at the side with numbers, like the actual ruler itself, you're influenced by the markings. Some people, they don't even realize that subconsciously they're actually measuring things when they draw random lines with a ruler. You're actually measuring. Your mind has a set distance in its head that it actually measured out without you even thinking about it. Okay? So preferably use the side without markings on it. So you flip it over and you make a mark. Now I know some of them have something scribbled in the back, just ignore it. If it's inappropriate, alright. Now, let's talk about the first construction. The first construction here is copying a line segment. It's drawing a congruent line segment. So let's mark that down. And I'll try to do a mock picture of what you guys are doing. So, alright. So construction number 1. Okay, it's called the congruent segment. That's the name of this construction. Okay, now let's talk about that word. That is a vocab term that we need to know, and that's the reason why I brought this up. What does the word congruent mean? Anyone know? Word congruent.
The same.
Yeah. That's a part of the actual definition. It's actually word for word. The word congruent actually means the same in size, shape, and measure. Now, you're probably looking and go, isn't that redundant? You said size, shape, and measure. Don't size and measure mean the same thing, or shape and size? Size is referring to actual proportions, so if you had a little model car versus the real car, that's proportion. They're almost scaled down perfectly to each other. So that's size. Shape is the actual overall shape. So do they look like the same object? And then measure is are they measured perfectly, exactly the same? All 3 of these have to be checked for something to be congruent to each other. So that's the idea. So, yeah, let's go right into this. So that's the idea. So what we're going to be doing is copying a segment. So drawing the exact same segment somewhere else in your paper without measuring it. Now I know that's silly because you guys got a ruler in front of you. Well, I can just measure it and then copy it somewhere else. But I want you to do it without looking at the side with numbers on it on your ruler, your straight edge. Okay? So here's what you're going to be given. So this is the part that we always have to talk about. So number 1, we have to talk about the givens. What are you given? You are given a line segment. That's it. That's all you're given. So you're given a drawing of a line segment. So on your paper, take your straight edge without looking at the numbers, take the straight edge, draw a segment, and let's label it, let's call it XY. Let's call it that. So I'm going to take my ruler. I don't have the possibility of not putting numbers, so I'm going to take my ruler. You can put it anywhere on your paper and draw a segment. Don't draw it like crazy long. Just make it medium distance. So here's my segment. I'm going to call it XY. Again, you can draw a pretty decent segment. I just don't want it going like all the way across your paper. You know, your compass here is limiting. You know, it can only open up so far. After that, it can't go any further. So just be cautious of that. For everyone, you have a little gear. There's a little like gear in the middle. You have to like spin it. I know for those brand newer ones, it's in the middle, and you just spin it and it opens up. Don't pull these, especially the metal ones. Don't pull them apart. You break them. It strips the gear rings, that type of thing. So use the actual gear to open it up. Okay, we'll all get the newer ones tomorrow. I wasn't planning on getting them today. All right. So what we're gonna do is, if you see your little segment, we're gonna copy that to a new spot on your paper, anywhere you want to put it, without measuring it, without actually using your ruler and going, okay, that looks like it's 2 inches, and then taking your ruler and putting it somewhere else in your paper and copying the 2 inches. Because it may not be exactly 2 inches. It's maybe just underneath it. So this is where we're going to learn how to do this. So we're going to talk about the steps. So our goal here, is to draw a congruent segment to the one provided. We're going to copy your segment to somewhere else in your paper, and you can put it anywhere else you want it without using a ruler and measuring it. That's what we're going to learn. It's a skill. And you're probably wondering, oh, this is easy. Yeah, it is. This is the first one. Eventually we'll learn ones that are crazy and super complex, and this is just a little piece of it. This is the middle of the problem. That's why we always start small. Okay, so step 1. Let's talk about the steps that we have to do. So step number 1, because I believe this one's only 2 steps. Step 1, number 1, you need to draw a line below the segment provided, or the segment given. So what do you mean by that? So you have your segment somewhere on your paper, right? You need to draw a line below it. A line. Now lines keep going. Oops, sorry. Projector's still on. Oh, okay. We'll have to continue tomorrow. Okay, I'm going to walk around. Leave your compass and your ruler on your desk. I'll walk around. I'll collect those. Be ready to come in here tomorrow. I'll hopefully hand out everyone's compass to them. If you have one of the newer ones, put it back in the little bag for me. Okay. Hopefully everyone will get a new one tomorrow. I was planning to use the plastic one for today, just to get used to it. Okay, we got to do some church today. I don't know if you guys moved very far because I just rearranged people just because of alphabetical order. So,
Okay.
We'll go through that here in a minute. Put that back up on the board.
New scene chart?
Yeah.
What? I just got used to that one.
Well, now you got to do it.
New scene chart.
So were our books supposed to be covered Friday or today?
Friday.
Okay, can I show you mine right now then?
No.
Yeah, hold on. Let me get some stuff done here.
I was all prepared.